Hello and welcome everyone. In this video, we are going to discuss the chapter 9, part 3, that is distributed transactions and consensus from the book Designing Data Intensive Applications. So in the previous videos, we have seen various concepts like causality, linearizability, cap theorem, total order broadcast, and we have seen how they are needed for a consensus. So let's first try to understand what does consensus mean. It is simply to get several nodes to agree on something. So, what are the different situations where we might need consensus? So, the first example is leader election. In a database with single leader replication, all nodes need to agree on which node is the leader. So, the leadership position might become contested if some nodes cannot communicate with each other due to the network fault. So, in this case, consensus is important to avoid a bad failover resulting in a split brain. And split brain situation is that in which two nodes believe that they both are the leader, and if that is the case, then they would both accept the rights and the data would diverge, leading to the inconsistency and the data loss. So let's look at the second example, that is atomic commit. In a database that supports transactions spanning across several nodes or partitions, we have the problem that a transaction may fail on some nodes but it can succeed on others. So we would want to maintain the transaction atomicity. That is, we have to agree that either all the nodes commit that transaction or all the nodes abort that transaction. So this instance of consensus is also known as atomic problem. So we will first discuss the atomic commit problem, and in particular we will discuss the two-phase commit algorithm because this is the most common way of solving atomic commit, and this is also implemented in various databases, messaging systems and application servers. So two-phase commit is kind of a consensus algorithm, and after learning this we will move to other consensus algorithms which are used in ZooKeeper, etc. So let's start with atomic commit and two-phase commit. So, what is atomicity? Atomicity means that if something goes wrong in the middle of making several writes, then the outcome of the transaction should be either successfully commit or abort. So, atomicity prevents any half baked results. And this is very important in case of multi object transactions or the databases that involve secondary indexes. So, in cases where the transaction executes on a single node, then the atomicity is commonly implemented by the storage engine. So when the client asks the database node to commit the transaction, the database makes the transaction's writes durable and then appends a commit record to the log on the disk. But if the database crashes in the middle of this process, the transaction is recovered from the log when the node restarts. And if the commit record was successfully written to the disk before the crash, the transaction is considered commit, otherwise it is considered as rollback. Thus, on a single node, transaction commitment depends upon the order in which the data was durably written to the disk. But what happens in case of multiple nodes? What if multiple nodes are involved in a transaction? So, in that case, it is not sufficient to send a commit request to all the nodes and independently commit the transaction on each one, because it can easily happen that the commit succeeds on few of the nodes and fails on another nodes, and this would violate the atomicity guarantees. And how this can happen? It can happen that some nodes may detect a constraint violation, some commits might have get lost in the network, some nodes might have crashed before the commit record was successfully written. So in this case, nodes become inconsistent with each other, and we should only commit once when it is certain that all the other nodes in the transaction are also going to commit. So let's understand more in detail about two-phase commit. So two-phase commit is an algorithm for achieving the transaction commit across multiple nodes, that is to ensure that either all the nodes commit or all the nodes abort. So how the two-phase commit ensures atomicity? Let's look at the various steps it undergoes to ensure atomicity. So whenever the application wants to begin a distributed transaction, it requests a transaction ID from the coordinator, and this transaction ID is globally unique. So application begins a single node transaction on each of the participants and attaches this global unique transaction ID with it. And if anything goes wrong at this stage, then the coordinator or participants can abort. Then when the application is ready to commit, the coordinator sends a prepare request to all the participants tagged with global transaction ID, and when a participant receives the prepare request, it tries and it makes sure that it can definitely commit the transaction under all circumstances. And if the participant replies as yes, that it can commit the transaction, then the coordinator, after receiving all the prepare request responses, it makes a definitive decision that whether it has to commit or abort the transaction. And once the coordinator's decision has been written to the disk, then the commit or abort request is sent to the participants. Thus, we cannot retract it. Then there are two crucial points of no return. When the participants vote yes, it means that it is promising that it will commit the transaction even if it encounters any error. And the second crucial point of no return is that when the coordinator decides that the decision is irrevocable. In this case, the coordinator must write the decision to its transaction log on the disk so that it knows which way it has decided the decision, and this is known as commit point. So now let's look at what will happen if the coordinator or participants fail. So let's see what happens if one of the participants or the network fails during the two-phase commit. So if any of the prepare request fails or times out, then the coordinator aborts the transaction, and if any of the commit or abort transaction fails, then the coordinator retries them indefinitely. However, what will happen if the coordinator crashes? So if the coordinator fails before sending the prepare request, a participant can safely abort the transaction, but once the participant has received a prepare request and it has voted yes, then it can no longer abort unilaterally because it must wait to hear back from the coordinator that whether the transaction was committed or aborted. So if the coordinator crashes or the network fails at this point, then the participant can do nothing but wait. And in this case, the state is called in doubt or uncertain. So let's take an example. A coordinator wants to send the commit request to two databases, and it has successfully sent the commit request to database 2, but it crashes before it sends the request to database 1. So database 1 doesn't know whether it has to commit or abort, and even a timeout here doesn't help because if database 1 aborts after some timeout, then it might end up in inconsistent state with database 2, which might have committed. Similarly, database 1 also cannot commit because we don't know what other participants have taken the decision. Thus, without hearing from the coordinator, the participant has no way of knowing whether it has to commit or abort. In principle though, participants can communicate among themselves to find out how each participant voted, and they can come to some agreement, but that is not the part of two-phase commit protocol. So the only way two-phase commit can complete is by waiting for the coordinator to recover, and this is why the coordinator must write its commit or abort decision first to a transaction log before sending requests to the participants, so that whenever the coordinator recovers, it can determine the status of all the in-doubt transactions by reading its transaction log. So now let's look at the fault-tolerant consensus algorithm. So consensus means that getting several nodes to agree on something. For example, if several people are trying to concurrently book a last ticket on the airplane or some seat on the theater, then a consensus algorithm can be used to determine which one of these mutually incompatible operations should be the winner. So consensus algorithm means that one or many nodes propose some value and the consensus algorithm decides on one of those values. In other words, consensus algorithm must satisfy the following properties. That is, the first one, uniform agreement, which means no two nodes decide differently. Second, integrity, which means no nodes decides twice. Then the validity, it means if a node decides some value v, then v was proposed by some other node. And the last, termination, it means that every node that does not crash eventually has to decide some value. So the uniform agreement and the integrity properties define the core idea of consensus, which means everyone decides on the same outcome, and once you have decided, you cannot change your mind. The validity property exists only to rule out some trivial solutions. For example, an algorithm is always proposing null value. And the last property, termination property, formalizes the idea of fault tolerant, which means even if some nodes fail, the other nodes must reach a decision. The system model of consensus assumes that when a node crashes, it suddenly disappears. So, in the system model, any algorithm that has to wait for a node to recover is not going to satisfy the termination property. In other words, you can see that the example of two-phase commit does not meet the requirement of termination, because in case of coordinator failure, we could not decide whether to abort or commit the transaction. So of course, in the cases when all nodes crash and none of them are running, then it is not possible for any algorithm to decide anything. So there is a limit to the number of failures that an algorithm can tolerate, and in consensus, it requires that at least a majority of the nodes to be functioning correctly in order to assume the termination, and termination property generally assumes that fewer than half of the nodes are crashed or unreachable. Thus, agreement, integrity and validity are always met even if majority of the nodes fail or there is a severe network problem. Now let's see how consensus algorithms and total order broadcast are related. So total order broadcast requires messages to be delivered exactly once in the same order to all the nodes. So if you think about it, this is equivalent to performing several rounds of consensus, and in each round nodes propose the message that they want to send next and then decide on the next message to be delivered in the total order. So total order broadcast is equivalent to repeated rounds of consensus. How? Let's see. Due to the agreement property of consensus, all nodes decide to deliver the same messages in the same order. Due to the integrity property, messages are not duplicated. Due to the validity property, messages are not corrupted. And due to the termination property, messages are not lost. So now let's look at how single leader replication handles consensus problem. So in single leader replication, the leader takes all the writes and applies them to the followers in the same order, thus keeping replica up to date. Essentially, it is total order broadcast. So if the leader is chosen manually and configured by the humans, then we essentially have a consensus algorithm of the dictatorial variety. Only one node is allowed to accept the writes, and if that node goes down, then the system becomes unavailable for writes until the operator manually configures a different node to be the leader. So in this case, the termination property of consensus is not satisfying because it requires human intervention in order to make the progress. So some databases do perform automatic leader election and failover, promoting a failover to be the new leader if the old leader fails. But in this case, we have to think of a fault tolerant total order broadcast solution. But we have a problem here. We need consensus in order to elect a leader. But if the consensus algorithms are total order broadcast algorithms, and total order broadcast is like single leader replication, and single leader replication requires a leader which requires consensus, so we are stuck in the loop. So how do we come out of the loop? So let's look at the epoch numbering and quorums. All of the consensus protocols internally uses a leader, but they don't guarantee that the leader will be unique. But they make a weaker guarantee that the leader will be unique in an epoch number. So every time the current leader is thought to be dead, a vote is started among the nodes to elect a new leader. Each election is given an incremented epoch number, and the epoch numbers are totally ordered and monotonically increasing. So if there is a conflict between two different leaders in two different epochs, then the leader with the higher epoch number prevails. But before a leader is allowed to decide anything, it must first check that there isn't any other leader with a higher epoch number which can take a conflicting decision. But a node cannot make judgment on its own. Instead, it must collect vote from a quorum of nodes. So every decision that a leader wants to make, it must send the proposed value to the other nodes and wait for a quorum of nodes to respond in favor of the proposal. The quorum typically includes majority of the nodes, and a node votes in favor of the proposal only if it is not aware that any other leader has a higher epoch. Thus, we have two different rounds, one to choose leader and another to vote on the leader's proposal. So this voting process is similar to the two-phase commit. The difference is that in 2PC, the coordinator is not elected and the fault-tolerant consensus algorithm only require votes from the majority of nodes, whereas in two-phase commit, it requires yes from each participant. And in consensus algorithm, they define a recovery process by which nodes can get into a consistent state after a new leader is elected. So now let's look at some limitations of the consensus. Consensus algorithm provides total order broadcast. They bring concrete safety properties like agreement, integrity, and validity to the systems, and they remain fault tolerant. But these benefits come at a cost. Consensus systems always require a strict majority to operate, which means we need a minimum number of some nodes to tolerate some failure. For example, we need minimum of 3 nodes in order to tolerate one failure, or a minimum of 5 nodes to tolerate 2 failures. So most consensus algorithm works on a fixed set of nodes that participate in the voting, which means we cannot dynamically add or remove the nodes. Consensus systems also generally rely on timeouts to detect the failed nodes. In environments with highly variable network delays, especially in a geographically distributed systems, it often becomes that a node falsely believes the leader to have failed due to some transient network issue. And this error does not harm the safety properties, but frequent leader elections can result in terrible performance of the system, and the system can end up spending more time choosing the leader rather than doing the actual work. So now let's look at how some of the membership and coordinator services work. So let's look at one of the coordination services like ZooKeeper. ZooKeeper uses total order broadcast algorithms, and along with it, it also uses various other features like linearizable atomic operations. So using an atomic compare and set operation, we can implement a lock. That means if several nodes concurrently try to perform the same operation, only one of them will succeed, which means the consensus protocol guarantees that the operation will be atomic and linearizable even if a node fails or the network is interrupted at any point. The second feature it uses is total ordering of operations. So, when some resources is protected by a lock or lease, we need a fencing token to prevent the clients from conflicting with each other in case of the process pause. So the fencing token is some number that monotonically increases every time the lock is acquired. So ZooKeeper provides this by total ordering all the operations and giving each operation a monotonically increasing transaction ID and a version. The third feature is failure detection. Client maintains a long-lived session on ZooKeeper servers, and the client and server periodically exchange heartbeats to check that the other node is still alive. Even if the connection is temporarily interrupted or a ZooKeeper node fails, the session remains active. However, if the heartbeats cease for a duration that is no longer than the session timeout, then the ZooKeeper declares the session to be dead. Any locks held by a session can be configured to be atomically released when the session times out. The last is change notifications. So not only one can client read the logs and values that were created by another client, but it can also watch them for the changes. Thus, a client can find out when the another client joins the cluster. By subscribing to the notifications, a client avoids having to frequently poll to find out about the changes. So let's look at some of the use cases of ZooKeeper. So ZooKeeper can be used in cases where we have to choose a leader in case of the failure in single leader databases, or in the partition databases. It can help to decide which partition to assign to which node. Thus, ZooKeeper provides a way of outsourcing some of the work of coordinating nodes like consensus, operation ordering, and failure detection to an external service. With this, it brings us to the end of the chapter, and let's summarize what we have learned. We have seen what is consensus, what are different consensus problems like leader election, two-phase commit, how we have to define a fault-tolerant consensus algorithm, and what are the limitations of consensus, and we have seen some real-world implementations of consensus protocols like ZooKeeper. So I hope you have learned a lot in this video and you have understood how we can deal with consensus algorithms and what other concepts like causality, total order broadcast, linearizability and consensus protocol are related with each other. Thank you.